Thank you all for joining us today. It's my pleasure to introduce Dr. Ayse Coskun, who is a full professor at Boston University and leads the large research team to solve problems towards making computing systems more intelligent and energy efficient. Her research interests lie at the intersection of design automation, computer systems, and architecture. She has led several multi-institutional projects, authored over 120 technical papers, and teaches classes in computer systems and software. And her research is widely recognized, and she has received several technical awards, including the NSF Career Award, Ernest Early Career Award, and an IBM Faculty Award. And she's also been an avid collaborator of industry and has received several patents during her time at Sun Microsystems. If some of you recall that, now it's called Oracle. And her research team has been committed to releasing their software and tools to the open source community. Dr. Coskun holds a PhD degree in computer engineering from UC San Diego and BS degree in microelectronics engineering with a minor in physics from Sabancı University in Turkey. It's my pleasure to have Dr. Coskun here with us today to share some of her research on AI for efficient and resilient computing. Please give her a warm welcome.
Thank you, dear Isha, and thanks for the invitation. I wish I could be there in person, but we'll have to do it another time when it's possible to travel. Thanks for joining the talk. I know that this is a rather interdisciplinary group, so if at any point something's unclear, feel free to ask questions. I may not see the questions in the chat window during the talk, but dear Isha, feel free to interrupt me.
Sure.
And so I'm going to talk about AI for efficient and resilient computing today. And I want to start with a little bit of a motivation why we look into this topic to start with. So machine learning is everywhere, obviously. All of you, or maybe at least most of you, work in something related to machine learning. Machine learning has many success stories, from image recognition to speech recognition to robotics to navigation and many, many others that would come to mind. And, you know, while a lot of these areas are still seeing innovation on a daily basis, there are a lot of mature fields that benefit from machine learning. So it's not a niche topic anymore. It's actually present everywhere, right? Now, when we look into computer system administration, so machine learning indicates you have a computer, right? So, you know, you run something on the computer and automate things. But if you look into computer system administration, basically, you know, taking a look at the system itself, we still see a lot of human-centric effort or expert-centric effort in maintaining and administrating these systems. So it may not necessarily mean that somebody has to physically go there and do something, which is also sometimes the case, especially in large-scale systems. But what I mean by expert-driven or, you know, human, strong human involvement type of wording is that expert would look at data, write some script, write some code, and then, you know, identify problems or identify how to better manage the system, do resource management, etc. So, you know, while of course, you know, this doesn't mean that somebody goes and physically does stuff all the time, but, you know, there's strong expert involvement in how computer systems are administered today. And this is all across the board, essentially. Now, for instance, let's say you identify that, you know, National Vulnerability Database says that there's this vulnerable package that needs to be updated with this name and with this package. And then this vulnerable file package and with this file size, etc., is going to indicate IBM SDK 5.0. And this is vulnerable, you need to update it. Great, you can go and your expert can identify this, go and write a script and then find all these files with the right file size and then say that, okay, these systems need an update, that you patch your system, great. But an update to this system actually is going to change some properties. So file name might differ, file size might differ. So basically these type of expert driven mechanisms to maintain computers become very inefficient and fragile and costly too. Basically, you need now people to be able to update their scripts and the like on a daily basis, especially on cloud platforms, for instance, where software updates happen multiple times a day. Somebody needs to be really on top of things and say that, hey, you know, the rules change now, the vulnerability is in this one, so I'm going to write a new script. Or, you know, previous resource management created this problem, so to solve that problem, I need to change this policy. So your experts, you know, gigantic team of experts need to be working really hard to solve this, and even then it wouldn't be efficient and resilient necessarily. So we need to move towards much more automated techniques in computer system design. So when people are designing computer systems, there are a bunch of goals. You know, I guess at a high level, computers aim to improve quality of life, right? So, you know, you can get mobile phones, you can do entertainment, you can get better navigation, you can get assisted healthcare, etc. So basically, they are here to improve your quality of life. They can advance science, like there are supercomputers that are running scientific computing simulations all day, and, you know, many other things. Computers are also good for making money. You know, you can solve important problems and, you know, sell your solutions, or you can, you know, do some Bitcoin mining and things like that and make money, and computers are good for that too. So can you still hear me?
Yes, we can.
Thank you. So while designing these systems, from chips to mobile computers to large-scale warehouse-scale data centers, performance is always a central goal. There is no computer design without a performance goal. You always need to meet the user's demand in whatever workload they are running, on whatever kind of system. It might be tiny, it might be huge, but performance needs to be a central goal. But in addition, these other goals have been becoming a lot more pressing over the last decade or so. Efficiency, because power efficiency is important, cost-wise, carbon footprint-wise, and the like, and, you know, scalability-wise. Security is super important. Obviously, I don't think I need to make a case. Secure. If you don't have security, you'll run into a lot of problems, and it could cost losing your users. It could cause privacy problems with breaches and the like. So security is a central goal now. And reliability. You don't want systems to crash all the time or fail all the time. Otherwise, you know, people won't buy your computers, or they'll have trouble with it, or, you know, they won't be wanting to use your software and the like, right? So these are now central goals as well, along with the performance goal. Now, how do we identify a problem when there's a problem either regarding security or regarding reliability or regarding efficiency, right? So how do we do this? Typically, in many other applications, if you want to debug a system, you want to get some data, right? So you want to maybe, if you are coding and if you want to debug something, you may want to print some statements, right? If you want to debug a database, you may want to collect some data again. So similarly here, there's a lot of data coming from computer systems. Some of this data is numeric data that is collected through what's called system telemetry. So there are many different layers of sensors, going from hardware sensors to different layers of system and software sensors in any computer system, that can give you from, you know, in a modest hundreds to thousands of different sensor data, typically on a second level basis. So you can get a lot of numeric data from systems. These data would then show you system usage, how active your CPU is, how many times your application accessed the memory. You can get detailed hardware usage data. You can get basically from different subsystems of the network, from storage, etc. You can get a lot of statistics, basically. So there is no shortage of numeric data in these systems. There are also logs. So you might be familiar with this. You know, when there's a crash on your computer, there's typically a log, and it's stored somewhere or sent to the operating system vendor or, you know, application vendor, etc. So these logs exist as well, and these keep a little bit more wordy data. Like at this time step, this event happened, and, you know, this is what I saw. It's not just for reporting problems, but it's reporting events essentially. There are files. So basically, if you are familiar with the Linux, for instance, file system. But generally all file systems have some some structure behind them, and there are a lot of files, right? So if you want to run an application, it comes with a lot of files in general. So this is also information. So it's not just the code that has information about whether there's a problem or not, but there's a lot of files, and this could be looked at potentially to identify a problem. And you can do more things like tracing. For instance, you can get a distributed application and say that whenever this part of the distributed application wants to create the service, I'm going to, print a statement about it. And then after that point, whenever this request is satisfied, I'm going to do another print and then measure how long it took. So this is called tracing. Basically, you instrument an application and collect targeted data. This is also available, although compared to, for instance, getting telemetry data, it's typically more costly in terms of causing some overhead, right? But all these data is available, and then there are other sources of data as well. Then the question becomes how to locate or identify a problem using this data, because now we are talking about terabytes of numeric data, logs from 10,000 systems or runs of applications, files in virtual machines or containers belonging to hundreds of different companies, and traces of distributed systems that can give you so much data that you have no idea what to look at. So clearly, this is not a scale where manual analysis could tell you a whole lot. I mean, there is data, there's no shortage of data, but even if you have the world's greatest expert, if you throw them this data, they won't be able to do much without some automation, right? So automated methods are essential so that we can get fast, repeatable results. We can identify problems rapidly and solve them in an environment where software and systems are updated so quickly that, we need to really solve problems quickly. Otherwise, we'll run into huge problems. Outages and bugs are costly. You might be familiar with, the Facebook outage, for instance, or Meta. So a lot of servers were down, and it's not just, Facebook users were upset about it, but many businesses got lost because, they were selling their products on Instagram and the like. Slack was down for a substantial amount of time. Again, it affected businesses. So outages and bugs are really costly. So you want to find what's wrong in your system really rapidly to avoid cost to your users and your companies. So machine learning in this general domain is a good fit because there's a lot of data with patterns in them. It's just, some automation is needed. And then machine learning is actually at a mature stage that we can apply with the necessary robustness and the like to identify when similar problems repeat again. So basically, in other words, if we are able to recognize a problem, we spend some effort, we determine that, this is problem X. I want to at least be able to say that next time I see problem X, I recognize it very quickly, right? So machine learning is a good fit to help solve these problems. And, then we can create broadly applicable frameworks that is not only, super specific to finding this file system problem in this version of the operating system if it's running on this specific machine. Instead of that kind of specific target, we can create broadly applicable methods that is, that is more robust across changes of the system, across changes of the software and the like. So I'll give some examples to help you convince, hopefully, to this vision that AI is really needed to automate the computer system management itself, in addition to helping with all these other areas. And I'll talk about how to diagnose performance problems, how to identify which application is running on a system, and then talk about fast software discovery. So the first example I want to give is to look into large scales and performance problems. Now, supercomputers or high performance computing systems originally were built with a lot of predictability. Now, so you would run the same thing and then get same performance. Now, over the years, because of mainly power limits being reached, the system architectures changed into having a lot more resource sharing than usual. Also, the number of cores increased, the types of parallel applications running on these systems diversified, and they became more complex. So with all of these things in mind, we started, even on these world's more predictable systems compared to your other kinds of data centers, we started seeing more performance variations. So there are many anecdotes on this. Some people say, 50% variation, some people say 100% variation, some people say 10x. So this is from our work. Basically, we saw on real world machines up to 8 times delay in job execution times when the same job was run on the same system. So this is a problem, right? I mean, I run something, it took me 10 minutes. Next time I ran it, it took me 2 hours. This results in poor scheduling, reduced efficiency, and clearly there's something affected my run. And these are expensive machines. I mean, supercomputers are built to help accelerate science. If something can be finished in a day, you don't want to keep it running for 2 weeks and block other things that are running, right? So there's a lot of additional impact if this problem is not solved. So much of these variations are caused by some sort of anomaly. We can think about them as anomalies. And it could be contention of shared resources like the network or the memory or some other shared resource. It could be some leftover orphan processes leftover from previous jobs that are clogging the system. There could be some hidden intermittent hardware problem that, hardware seems to be working, but every now and then is doing something weird. And these are creating system anomalies. Now, if I know what anomaly is there, then I can do something about it. So that's what we wanted to work on. And our intuition was that anomalies are going to manifest themselves in performance metrics that are coming from this telemetry, like OS counters, system utilization, network hardware counters, storage subsystem counters, and sensors, and the like. So this is basically time series data, and it's multivariate time series data. So you have a whole bunch of sensors, and you can sample them on second level intervals typically. And this is virtually in any large system is collecting this data already. It's just nobody's doing anything about it typically, but data is there. So it's not a problem to collect, and it doesn't really slow down the system because it's done part of a particular subsystem. So quickly, you can think about it like you are collecting hundreds or thousands of sensory data per second per node, at least, and you can actually get more detailed data if you want through like per core level on each chip. But even just thinking about per server, we are talking about terabytes of data being generated per day and hundreds or thousands of metrics. So that's the challenge. But the advantage is data is supposedly pretty comprehensive because you're collecting a lot of rich set of sensory data at the end. And this is, like I said, it's available. Everybody's collecting it. Some data is even released publicly. So data is there. So you can do something about it if you apply the right technique. So what we wanted to do is to create an automated analytics framework that uses this numeric data. And the idea is to learn the anomaly characteristics for known anomalies using labeled historical data. And then next time I see it, I want to recognize it. So basically, for source of data, we need some healthy data, but we also need some past anomalous run that is already labeled by system administrators or users. Because if I know the label, then next time I can diagnose it. So for this reason, we started with doing some controlled experiments. With known anomalies, you have your system, you run your applications under healthy scenarios, under your anomalous scenarios, and then you generate features, you create a model, and then at the end, the system is supposed to say, hey, there's a memory leak on these nodes, or this is healthy, or there's a contention on this particular resource. So this is what we created. Now, going through some of these steps. So if labeled data is available, you can use it, but often labeled data in terms of showing which telemetry multivariate time series data is belonging to what type of anomaly specifically. This data is rare compared to the size of the gigantic data sets you have. So one method we used was to insert synthetic anomalies that mimic the original anomaly so that we can train the system with known anomalies. And these synthetic anomalies, we generated a small subset of them based on discussions with system administrators at national labs. And we used it for creating labeled data. Basically, then each anomaly stresses some subsystem, like memory anomaly, network anomaly, etc. Again, based on what anomalies are prevalent. And then we run a representative set of applications, and basically with all known conditions, and generated features based on these time series. And the time series data includes, like I said, information about CPU, memory, etc., collected from hardware or software counters. And then these features are that we are creating basically retain the characteristics of the anomaly and the healthy data. And because this is multivariate time series, I mean, a bunch of techniques are usable. I mean, some of you might be doing research in time series analysis. What we did was to convert each time series into a set of features, basically, and we used some statistical features to do that. So you get this time series sampled at every second. It could be a small window or a larger window that could be adjusted depending on your needs. But per window you are looking at, we can collect the minimum, maximum, average, different percentiles, standard deviations, skewness, kurtosis, etc. So we have this about a dozen features that we are collecting to convert the time series metrics into a smaller set of features. So this enabled compressing the data while retaining the information in the data about this time series. And then we did some feature selection, applied Kolmogorov-Smirnov tests, and then through the Benjamini-Yekuteli procedure, we basically determined the features that are most relevant for the specific anomalies we are testing for. So initial work, actually, we just didn't do any feature selection, just threw all the features. Eventually, as we started working with systems that collected a richer data set, like going from hundreds to thousands of different sensors, we saw substantial benefits in doing some feature selection. Actually, our most recent work that hasn't been published yet is doing better feature selection, and it's helping even more because, like I said, there's no shortage of data. There's ample, and actually people see the value in this, so they collect more and more data. So doing smarter feature selection tends to give better results in terms of your overall prediction. And then once we have all these features with the controlled data set, we can train our machine learning model, which is going to then predict upon seeing similar data. Upon receiving the similar same input of features, if it sees a similar pattern, it's going to say things like, hey, this is healthy, or this is memory leak, or this is network contention, and the like. We tested out this with a number of different machine learning methods. In general, tree-based methods like random forest worked really well. AdaBoost also did quite well. But proposing a new machine learning method was not the focus, and it actually was not necessary in this work. So we used also some tweaks at runtime. For instance, we wanted to use a false positive filter because sometimes there are glitches. Like for a second, the system says there's an anomaly, but then it says, no, it's healthy. So to avoid triggering the user too often, we use some false positive filters, for instance, to only alert for a problem after seeing the same prediction a few times. These are necessary, these type of tweaks are typically necessary for increasing usability of the techniques. Because imagine this, you are on a computer and the system keeps telling you every minute there's a problem. The first thing you would do is to turn off that utility that gives you the alert. So you don't care at that point, like you are so annoyed that you don't care if somebody is attacking your system. It's just you can't work with somebody alerting you every minute, right? So we want to make sure that these systems are usable at the end, so they only predict when the system is really confident, and then maybe other things can be flagged for looking at it later. So these are important balances for people to be able to use these techniques, even as user or also as administrators. All right, so I mentioned synthetic anomalies. What are these synthetic anomalies? So like I said, we put together a small set based on discussions, based on literature search, but actually discussing with people who maintain and run a lot of stuff on supercomputers helped a lot. So based on what they said, we created memory leak, memory intensive processes, network interference, cache interference, and leftover orphan processes. These are the types of anomalies we initially created, then updated it further to make it somewhat more comprehensive for all different subsystems, to occupy the CPU, cache, intensive workloads, memory bandwidth, anomalies. There's a lot of different memory anomalies that are out there. Basically things that consume the memory a lot, or just high demand. They have high demand on the bandwidth. They cause others to slow down, especially there are memory leak problems. So we wrote different code for these things. And we also created some network anomalies and some IO anomalies. And we packaged all of this into an anomaly suite called HPAS, HPC Performance Anomaly Suite, and released it. You can use it. You don't have to be an HPC researcher. If you are looking into creating some stress conditions, some anomalous data for any computer system, including in mobile, you can, we believe you can use this type of code. So this also basically gave the community an opportunity to standardize some of these experiments. Like I mentioned a few times already, there's no shortage of data. There is, however, immense shortage of labeled data in computer system domain. So having these type of suites that enables the community to replicate experiments is tremendously important. So part of it is how to apply machine learning so that, you know, you can go and figure out like what's the best framework, what's the best specific machine learning technique, what kind of data, like what kind of features, etc. But at the end of the day, you also need mechanisms to be able to experiment with all of this. And while data is available, labeled data is not. So what are you going to do about it, right? So these type of benchmark suites are really useful for growing the research in this community. So I think there are more opportunities to create benchmarks or suites like this. So anyway, showing some numeric results. So we got really good results, basically training with a small set of representative applications. And in the test set, then we didn't have one or more of the applications typically. And similarly, we did test with, you know, having all anomalies or having unknown anomalies, etc. This is showing a more basic results. Basically, you know, you do separate the test and training data, but you assume you are able to train with a representative application set and a representative anomaly set. And then in that case, you actually, using a technique like random forest, or using the framework that I described, you can detect successfully over, you know, 98% of the injected performance variation. So this is a very strong result, right? So there's a lot of promise. Now, one might ask, okay, is this labeled data available? Is this realistic, etc.? And I'll answer those questions in a bit. One other important thing is, like I said, it's not just your F1 score, like how accurately you can predict things, but also you need to maintain a very small false alarm rate. It's actually, I would claim that having a small false alarm is more important than having, it's more important than your miss rate of missing anomalies. Because if you, like I said, if you keep bugging the user or administrator for problems that did not exist, the first thing they are going to do is turn off your automated system. So you don't want that to happen. So having really small anomaly or a false alarm rate is really important. I see something in the chat window. Do you want to ask now or later?
I think the question is, can GANs help in generating data to train these systems?
Can GANs help generate data?
Yeah, to train these systems.
It might. I mean, I guess you do need some set of labeled data to start with. And then you can techniques like GANs can expand that data set to generate more labeled data. Is that the kind of thinking you were thinking? Maybe.
I think it's a student who asked, Fatima.
Yes.
You want to?
Okay.
Yeah, I was thinking the same thing. Like if you have some data to start with, since labeled data is scarce, perhaps can generative adversarial networks help in generate more data?
Yes, exactly. So this is an excellent question, and actually we've been looking into this label propagation techniques or GANs-based techniques, etc. So far, we didn't really get amazing results, but we are still working on it because it's a problem. And it depends on how you construct the problem. You can expand the data and create more labeled data based on few labels, or you can design like few-shot learning type of methods with less data. I'm going to talk about a little bit of some successful results we got, but this is definitely ongoing research and there are more things to try. Excellent question. Thank you. All right. So actually, the next slide starts discussing this. Normally, there's a lot less real-world data in terms of labeled data compared to what we've been initially experimenting with. So we designed a semi-supervised anomaly diagnosis framework, which is, the general idea is the same. Like we have multivariate time series data. We to create features, we train a model, but at the training part, we have very little training data. So what we do is basically we use some unsupervised pre-training that is then followed. Basically, we do some autoencoder based stage before supervised training to prepare the data, and then we apply supervised training with our known labels. And this one, when there is really little labeled data, for instance, when we were training with original data set that I was just showing you, we had like 5 different anomalies plus healthy runs of 10 different applications, multiple runs, this type of rich data, right? When we assume we knew all the labels. Compared to that scale, for instance, when we just say, okay, what if we have only 1% of this data? Then this type of semi-supervised framework did better. However, one thing that was interesting is that the original method didn't do so bad either. So there's actually a crossover point where if you look into this graph, there's Proctor, which is the semi-supervised method that uses the autoencoder followed by the supervised learning engine. And the RF one that's in orange is actually showing the technique that I was just talking about, like fully supervised method, right? So when the data labeled percentage is really low, there's a lot of advantage actually to using this type of semi-supervised approach, or basically a method that is aware of the fact that you have little data. But as you increase the labeled data percentage, at some point, the fully supervised method that is just training with the same amount of data, knowing, nothing, applying nothing else, catches up at some point. But an important difference that we observe was that anomaly miss rate for the method that we generated using autoencoders first and then supervised learning, the anomaly miss rate stayed lower. Basically, overall, it gave better performance in our opinion. There is more research to do in this domain. Like I said, we've been looking into several different things like label propagation. Should we do few shot learning? Should we do online learning to just, as data comes in, we do better predictions, etc. And there are open problems still. What to do with little labeled data and lots of unlabeled data. And this is an important challenge that we are looking at right now. Okay. But initial results with this Proctor approach was quite promising overall. So one other focus point in this project has been to demonstrate all of this, not just with real data from real systems, but actually running on real systems. So many machine learning models, many machine learning based frameworks consume a lot of compute power and a lot of memory. You might be aware of this already. There are actually now efforts to green the AI. So many people are running so much AI stuff on large scale clusters, it's actually creating a substantial carbon footprint. So, it's not just an issue of performance that, things run for a while, but it also has an important energy footprint. So it's at that level. So going back here, then you can think about, okay, I want to have a machine learning model to basically do anomaly detection on this high performance computing system that is serving a lot of critical applications. So I better do a good job in doing this at scale and fast and without generating overhead, right? I mean, some overhead could be acceptable, but it needs to be small enough so that it's not actually impacting the other important scientific workloads that are running on the system. So machine learning can be costly, in other words, and we need to keep an eye on this while we are creating systems to deploy on real world systems. So we got our original framework that I showed you, the fully supervised one, and then we deployed it on a 1500 node production system in collaboration with Sandia National Labs. And we did quite a bit of work around it in terms of providing the right kind of interfaces to be able to use it. That's the other challenge. Like one is scalability that includes running time and overhead. And another thing is giving the right type of APIs to users so that they can actually use it. So they can actually come and determine what anomaly they want to detect, and they can actually understand the results, right? This was joint work with Sandia engineers. So we had our code reshaped for offline model training. We added some wrappers, etc., to make things more efficient. And then at runtime, basically, it was querying the monitoring server to get the data, and then applying the trained model to do predictions on the anomalies. So this is working, and it can be used basically, and we have it open sourced as well. So one challenge that I'm not going to talk about now is also explainability of the models. Now, I mean, typically when you look into explainability literature, people are talking about explaining deep learning frameworks, typically, right? So generally, when you do random forests, the community tends to think that that's already explainable, which is true to some extent. But think about this: like, you are asking a computer system administrator to deploy a machine learning framework that's going to make predictions on anomalies, and this person is supposed to take action on this, right? So rather than just doing a binary, hey, you have a problem and go look into this, or like, no problem, they want to actually understand, like, okay, you are predicting memory leak right now, but why? You know, so that kind of explanation becomes pretty essential for the usability of this type of system. We've done some work in this domain for explaining time series based machine learning methods, and we have a publication out and also some code that's released. If you are interested, I can give you the link, but I won't cover it now. But I just wanted to mention that if people are interested in this explainability or interpretability domain, there is a lot of potential in even creating things that can explain relatively simpler machine learning methods. So on the production system, we got good results that made everybody happy. I mean, depending on the system, though, it's hard to claim it's reaching a certain F1 score at all systems, at all times, for all applications. Obviously, it depends on what you are training with. But overall, our results are consistent in the sense that we can do an excellent job determining whether something is healthy or anomalous. And then the real challenge is determining what anomaly is there. And over there, some anomalies are easier to detect than others. And this is also a function of the anomaly intensity. We did experiment with different intensity of anomalies. And sometimes it's affecting the system in an obvious way, like your application is running really slowly. And sometimes the anomaly is subtle, like it's affecting something, but the user is not really seeing too much impact. The good thing is a machine learning framework can detect anomalies really early without really, expecting a catastrophic issue or some system crash or some really delayed runtime. On the other hand, its success is really dependent on how much the anomaly is manifesting itself. So long story short, memory leak, memory bandwidth is very easier to detect compared to some, just CPU heavy anomalies on this production system. So what else can we do other than debugging performance variations? So I spent most of the time in the first part. I'll talk more at a high level in the next two examples to give you some ideas, but won't go into as much detail. So one problem we looked into was to identify an application, and as opposed to identifying something that's anomalous. So you want to sometimes detect an application, like what's running on the system, because you may not know it. Users, even if you see what's being submitted as a job, users may, intentionally or unintentionally label their stuff without descriptive names. When you look at a supercomputer, you see a lot of run me one, run me two type of things that have nothing to do with application names, right? So, I mean, you want to know what's running on a system to better manage it, to prevent wasteful apps. You want to prevent vulnerable or buggy apps if there are known problems. And also there could be that there are malicious or fraudulent applications that you are banning on your particular system, right? And there are some interesting examples. For instance, Bitcoin mining with a supercomputer. Somebody was caught doing this and then they got suspended. This actually happened multiple times. Initially, it happened in national labs, and then it happened at a university. So, one takeaway from this talk: if you are going to do Bitcoin mining, don't do it at a supercomputer. You'll get caught. Here's another one from the media: nuclear scientists arrested for Bitcoin mining plot. Again, they were using supercomputers. So, anyway, so these are some interesting and somewhat funny examples, but overall, like I said, detecting what types of applications are running on a system is a common practice to improve performance, energy efficiency, and there's a ton of application-aware management schemes out there, but then, they don't necessarily have a mechanism of identifying the application. So we used resource usage fingerprints. So basically created fingerprints based on the telemetry data. And just, if you do simple clustering, you already see, like in this graph, these are different applications, and, it's basically cluster distance graph. Unsupervised, it shows some promise that applications actually have different fingerprints in terms of what kind of telemetry they generate. So it's not perfect, like you see the same application multiple times here if you're carefully looking median these twice, appearing twice, but clustering data shows that there's some promise that applications differ in their resource usage. So we used a very similar framework to the one that I described based on the machine learning framework for anomaly detection, and we call this taxonomist because it's doing an application taxonomy. And this is essentially the same kind of framework. I'll just focus on what's different. So previously, this is what we did, right? So this is like healthy, anomaly 1, anomaly 2, and then we just classified everything, which worked well for anomaly detection. But for application detection, the problem is that if you do this, you need to assume like all the applications that are ever going to run on the system, or you need a good chunk of it, which is never the case. Even in the most controlled system, like in a supercomputer large scale, compared to cloud, where the applications numbers might be even larger, there are a lot of unknowns. So we changed the model. So as opposed to doing this multi-class classifier, we wanted to switch to a one versus rest classifier, where we say that, this application exists, and then this is the rest of the world, right? So basically we want to search for these few known things among a large set of unknowns. So as a result, we changed the machine learning design, but used a very similar framework overall. So basically, you want to only detect an application if you have high confidence for that application, and you don't want to create this multi-class classifier with where you have an ocean of unknown applications. All right. So I'll just, some brief results. We got really good F scores in identifying applications, and, we trained with 10 and then tested with 11, some unknown application. There's obvious things like if you train with 1 and then test with a very large number of unknown applications, then the F scores drop a little bit. But because of the way we designed the machine learning framework, we were able to actually find few known applications across a large amount of unknowns. And we used real world data. This is Volta, used to be a supercomputer at Sandia National Labs. It's got updated recently. Now there's a different machine. But, looking at that, we were able to determine some cryptocurrency miners that we put in there, basically. I mean, nobody was doing really cryptocurrency mining at national labs in doing this experiment, but we ran some software for it, and we were able to find them among a lot of unknown applications. So maybe the last bit in the next few minutes I want to wrap up is numeric data, telemetry data is not the only data that one can look at. Actually, there's a lot of other data that is potentially really rich in terms of providing you information about what's going on the system. And maybe I'll just move a little bit here. So one data is basically looking into file names, like I mentioned, but then if you want to write scripts, then this is fragile, and then you have to write a new rule all the time, and it becomes fuzzy and fragile. So what we did in terms of looking into file names was to do something that's more efficient. So discovery by example, for instance, is used in many domains. Like, here's a dog picture, and then this is the example. Here's a few dog pictures, and then, here's a bunch of images, go find the dogs, right? So this kind of discovery by example is done in image processing, in videos, in sound processing, etc. But in systems, what is the data? So what we did was to create fingerprints out of file names when a new application is installed. so that, you know, your application on the cloud, for instance, is going to maybe install 100 files. We would get that file list, anything that's new that didn't exist in the system before, and hash them into a small fingerprint, and that becomes something that encapsulates the system's data, the application installation data. And then if you keep doing this, you can create a lot of fingerprints and learn what the fingerprint looks like for different applications. And there, you know, you can have a little database that is keeping fingerprints for known applications. I mean, you want to do that typically because you know, you want to protect against some known vulnerable applications, or there might be compliance issues that you don't allow certain type of applications on your system. And then, you know, using machine learning, when somebody is installing something new, you can get their hash, get their fingerprints, and then run it across the fingerprints you have using machine learning and say that, hey, you know, you have this application that's vulnerable, you need to update this, or you can't run this on my cloud. I'm not allowing you to run an email client on this cloud. So you can actually do these type of things. So it was really nice because, you know, we went from, as opposed to using numeric telemetry data, we went from file names to creating these vectors and then hashes that encapsulated data, basically created little images of the systems. Then we could basically use machine learning to navigate. Okay. So along these lines, there are many open problems, and one recent piece of work that we are doing is taking this to the next level, basically applying AI for cloud operations. And similar to high performance computing, modern cloud platforms are far too large, far too complex, and far too noisy for doing any meaningful manual debugging. And if something is crashing, the best thing you can do is just look at a bunch of log files to figure out what's going on. And, you know, once you figure out something, you can write a script to figure out the next time it shows. But like, people are going to update that software probably tomorrow, so your script is going to be obsolete in a time frame of days. So this is really common story in the cloud. So it's even more challenging compared to supercomputers, where the software development is somewhat more stable. So complex cloud problems require adaptive tools, and they need to be cross-layered, because now, in addition to telemetry data, cloud has many levels of software. So there's the infrastructure data, there's platform layers. On top of that, there are applications. Some clouds are, the people come and just deploy their Jupyter notebooks today. So there are many levels of software interacting and many layers of data. So many different kinds and layers of data need to be aggregated and pushed into an analytics engine, and hopefully some, you know, interesting and meaningful insight can be given. So this is the new project that we just started like really last month, based on our expertise in this domain in doing applied machine learning for HPC and cloud, but with you know, a lot more ambitious goals in making this work for real world cloud systems now. And our goal is to improve performance, resilience, and security in a low cost and scalable way. If you are interested, like I said, there are a million open problems, and we'd like to discuss if you have ideas. So some takeaways from the talk would be, I showed some examples of doing automated analytics for large-scale systems based on numeric data. I briefly touched upon that you can look into file names and software changes to detect for the applications running. There's a lot more things one could do looking at different layers of data. So far, we looked into performance variation problems at the system level and application level. And once you start looking into file names and the code itself, you can actually do many more things. You can detect applications and functions even at development stage that are problematic and that need to be updated. Basically, even before things are running and creating anomalous fingerprints or whatever, right at the installation or deployment stage, you can actually determine things and give feedback to the developer or to the user. So there are different layers, and obviously, the earlier a problem is determined, it's really good, because if you can detect a problem before it runs on a cloud, everybody is happier. So this shift to the developer side is really valuable, but of course it comes with challenges as you don't have numeric data and you have code and data like file name, etc. to look at, but you don't really have a lot of numeric data. So the types of data are sometimes also more challenging. Typically, it's harder to look at textual data and compared to numeric time series, for instance. So I hope I interested you in this topic. We are strongly advocating for more intelligently designed machine learning to improve and automate system management itself. And right now, significant outages occur that causes major loss of profit. And there are problems due to widespread vulnerabilities, and these are all incredibly common, as I'm sure many of you experienced firsthand. So automated analytics can help tremendously, but the problem is not as simple as just getting the data and throwing some machine learning on it. There are a lot of interesting challenges in which technique to apply, how to scale it, and how to especially make things work in complex multi-layered systems. So with that, I'd like to conclude the talk to leave room for a few minutes of questions. And this is somewhat, before the pandemic times when as a group we could get together, this is a picture we took at the time. So I have 7 PhD students right now and several undergraduates and some master's students. So we worked with industry, and we still work with IBM and Red Hat currently on these topics and Sandia Labs. And some of my collaborators are shown on this slide as well. So you can find us on the Peak Lab website, and all of our software also is on GitHub, but there are links from our website as well. So with that, if there are any questions, I'd like to hear from you. Thank you.
Thank you, Ayse. That was a great talk, showcasing the applications of machine learning for system management. Please feel free to ask the questions either in the chat or raise your hand. I see Dakai, do you want to ask a question?
Yes. Thanks, Marisha. It's a very nice talk. Dr. Coskun, thank you very much. It's very informative. I know that your work are mainly on the high performance computing, the production systems. And my first question that I have is, so when you detect an anomaly, it may come from different part in the system. So how do we distinguish between the errors that potentially happen in the software application, or it is because of hardware failure?
Oh, that's a great question. So essentially, right now, the kind of framework we designed was agnostic of where the failure is specifically happening. It didn't really care about it as long as somebody gives the system, like, here's the telemetry collected during this time, this type of fault or failure happened. So that said, it can potentially detect hardware failures or software failures as long as, like I said, these errors manifest themselves in the telemetry, and they do typically, and then somebody has the labeled data. But one important thing to note is that often hardware problems that result in faults generally, or system crashes, are easier to detect and diagnose. I'm not saying they are easy, not necessarily, but generally they are easier compared to something like detecting if there was contention in some shared resource somewhere, or detecting if file system had an issue, so somebody pounded on it and it crashed, kind of things. And the reason is typically hardware problems. Many of the hardware problems manifest themselves often in particular subsystems very strongly, as opposed to some little software bug that might be affecting the telemetry data every now and then. So like I said, generally it can be applied to a broad set of problems as long as they have some signature in the telemetry data. But typically the types of problems we want to look at were like a little harder to detect, more subtle problems. Does it make sense?
Yeah, it makes sense. So my second question actually relates to your last topic on the AI for the cloud operations. I think one part of that is because of the application have performance anomaly, as you mentioned, sometimes it run really slow. And I think one part that we have done a little bit of work on the performance prediction in their VM, which is the application in VM.
Yes.
So we use a profiling technique, and each of the VM can basically profile at runtime to see whether I have contention with other co-running VMs or co-running application there. And then probably, maybe I can talk to you later on for more detail there. And actually, I have another question on their anomaly detection in their small system. For instance, I know that you have worked on a PC complex system. So if you have the embedded system on their failure, and what is the best feature that you think that we can use to predict their reliability or availability at runtime? Are we still looking at the performance counters or some other features?
Great comments and questions. Thank you. For your previous comment about profiling, definitely I'm interested to hear more. So basically, profiling or application of workload aware resource management is one area for doing better, more intelligent cloud operations. Our work will start from actually, as opposed to resource management, we'll start more from software discovery. Basically, when people are deploying, making changes to their software and deploying, and then at some point it crashed. Why? Like I was just running this data science application and everything was fine. I updated something. Now it runs for 2 hours. What happened? So these type of problems. So it's going to be a little bit different. But there's certainly interaction because, like you said, resource management is also important, and it's also part of the ops functionality of the clouds. It's part of the operations. And regarding the question about embedded systems, the telemetry data, getting data from sensors also exist in embedded systems. So it could be performance counters exist on any CPU, but also operating system counters and such. So this could be done, basically collect the telemetry data and look into it. Of course, it needs to be done in a more frugal way because, for instance, right now on a supercomputer, I don't have really problem about file size. I mean, like I can just put the telemetry data somewhere. So and things like that, it needs to be scaled down to it needs to be a little data problem rather than a big data problem. So it needs to be compressed.
That's great.
But one other thing that I thought, and I never got around to really doing it, was that this type of application-specific analytics for embedded systems could be really useful because you know what applications are installed on your phone. There's no surprise. It's not like a desktop. On your phone, you actually, it's not like a server. You have exactly a finite amount of applications, and we could actually determine what those applications normally do in terms of their resource usage and flag when they are doing something abnormal. Like I play a game, it's not supposed to do in networking. It's pretty easy actually, if you look at telemetry, to determine if, hey, this application is normally not using the network subsystem this much, it's doing something off. And this type of flags could really help, especially wasteful or malicious processes running on embedded system.
I see. Okay, great. Thank you very much.
Other questions? So Ayse, I had a question on your first part where you were talking about using, you're extracting all the, if you look at that slide, you're extracting all these features and trying to use ML models. And you've talked about you showed some really good results on the performance as well, right?
Yes.
And you looked at even false positives. I was curious as to how the model's inefficiency itself plays a role in this case, in a sense, how well it is able to predict, right? You talked a little bit towards your second part where you probably need to know a little more about the model and have explainable models as to why they're working or how they're working to see what is the rate of false positives or false negatives you could have in this scenario. So are you looking into the robustness of the model itself here, or you're more interested in looking at the entire framework and robustness of your system management?
That's a good question. So, I mean, we haven't done in-depth studies on the robustness of the machine learning model itself, but that could be done certainly. So generally, it's been very applied until recently. So we were like, okay, you know, let's try a whole bunch of things and then find. That's how it started basically. Let's try different types of machine learning methods that are, you know, relatively low cost, and then see if we get good results. We got good results, and then I showed results with some machine learning models. This is not comprehensive list of everything that was ever done. So we did do some more complex stuff at some point as well, for instance, like neural networks and the like. Overall, we wanted to find this balance of a method working well enough for our problem, and then it having lower cost and relatively easier to explain kind of thing. However, studies would definitely support in terms of like, what is the robustness of this particular technique for this problem, why it's performing better with this kind of data. And these are all open problems. We didn't really do a deeper dive. Now, actually, the latest project that we, Sandia Labs and my lab, started jointly is with this problem of being able to do things with little data. We can't help but look more into, okay, what's going on? You know, why is this technique doing better here, and why is this technique doing worse here? What is he actually? What is the technique actually learning? Is it learning the right thing that we wanted to? So we started looking more into these things, like you said, and that includes keeping an eye on robustness as well. So hopefully, next set of results is going to shed a little bit more light on what works better with little data.
Okay, that's helpful, I think. Yeah, there is a lot of opportunity there, I think.
I think so.
One last comment. I've observed, I think you made this comment in your second part about applications, that they're so diverse, and you've looked at some applications, right? It's very hard to kind of profile maybe based, or like tailor your model based on the application. I was thinking more based on your first part, like the framework that you've just shown. It could be pretty application agnostic if you're able to profile the characteristics similar to how you do in your computer architecture models, right? If we do extensive profiling.
Yeah, that's a very good question, because you're right. I mean, actually, something to highlight is that we wanted to create a framework that's agnostic of the application while creating the anomaly. So even though we tested with a small number of applications, relatively speaking, because there are, you know, thousands or tens of thousands of applications in the supercomputing domain, and we tested with dozens of them, not hundreds of thousands of them. So it's a modest experiment at the end. However, we wanted to learn the signatures of the anomalies in an application agnostic way. So therefore, we think that if you train with only one application, that's not enough. But if you have a representative set of applications, which means that you should have applications of different kinds. One is doing more networking, one is doing more CPU, one is doing a lot of messaging between different nodes. So if you have a representative set of applications stressing different kinds of subsystems, different behavior at runtime, and then you train with them in a healthy way, and then you put the anomalies on them, or you have the anomalous data on them, then we believe it's possible to actually capture the anomaly signature rather than capturing the anomaly / application signature. So I don't think it requires a large set of applications. It just requires a representative set of applications.
Right.
Because even though there are many different applications, at the end, what matters is how they leverage the underlying network, and then how, this anomalous behavior compared to normal differs, right? So that distinction is what determines whether you can catch it again next time you see the anomaly.
Right. Thank you so much, Ayse. That's a wonderful talk, and shows a great application of machine learning models. And hope we get to see you in person next time.
Thank you very much, and thanks everybody for participating. I hope you found something interesting in the talk. And if you have any questions, check out our website, peaklab@bu, and you can always email us questions. Thank you.
Thank you. Have a great weekend. Bye.
You